Well, good morning, ladies and gentlemen. Mr. Dorfler back with yet another daily dose of Dorfler. All right, we're back at day number 2. Hope you all have your noggins warmed up from yesterday. Yesterday, we talked about momentum, okay? And so we're going to take that concept of momentum and add it to our next topic of section 1. And that is going to be impulse, okay? And more specifically, the impulse momentum theorem. So what is an impulse? Well, an impulse is the product of the force and the time over which the force acts on an object, okay? How long do two objects have in contact, and at what force are they contacting each other with? Okay, that will be our impulse. The impulse momentum theorem is what we are going to be focusing our attention on today. We're going to be looking at that concept of impulse and how it impacts the momentum of a certain object, okay? And this theorem states that when a net force is applied to an object over a certain time interval, the force will cause a change in the object's momentum. So here is your next formula that you need to add to your formula sheet. We have force times delta t, or the change in time, or the time frame that they are in contact, is equal to a change in delta, or a change in momentum, or delta p. But delta p also means, or can also be solved by mvf minus mvi. So really what you want to do for your formula sheet is this. F delta t is equal to mvf minus mvi. That's what you really should write down, okay? So we're going to be using that formula as we get into our calculations today.
Here's what I found.
Oh, I'm not certain why my watch just decided to talk. Sorry about that. So other examples of where we can use this impulse momentum theorem is when we need to calculate stopping distances and stopping times, okay? Where might this be a valuable asset? Well, think about vehicles. Okay, vehicles are always looking for the best products in engineering so that their vehicles can stop in the shortest amount of time, as well as the shortest distances, because if we can stop shorter and quicker, we tend to be a little safer out there on the road. We can also say that force is going to be reduced when the time interval of an impact is increased. You might see this in certain examples. If you have a trampoline, and yes, my daughter's got a trampoline for Christmas. Not too happy with it, but, trampoline sends the jumpers up higher into the air than their normal jump would be. But also, as they land, that trampoline also cushions their impact that they're having and causes them to slow down over a much longer distance than if they had jumped down onto, say, solid ground, okay? So we also see examples when we look at this right here. We have, on the left-hand side, we have an egg that is falling. On the right-hand side, we also have an egg that is falling. The difference here is what the egg is going to land on. In picture A, it's going to land directly onto a hard surface or a plate. In picture B, it's going to land into a nice, soft, cushy pillow. So in A, on the left, when this egg impacts this plate, it's immediate. There is a great amount of force at a very short amount of time of impact that it causes the egg to break. On the other hand, when we have a pillow here to cushion the egg as it falls, once that egg hits the pillow, that pillow begins to sink, and it slows that egg down and reduces the force. So it takes a longer time for it to come to a stop. So, you also see this when you brake in a vehicle too. You stop suddenly, you lurch forward like this. If you brake gradually, everything is nice and peaceful, okay? So, very important aspect when we're talking about moving objects. So this video right here, I've included into today's post. It's about a 5-minute video. He's a good person to listen to. A lot of quick, good, additional tidbits of information. Recommend you watch it. You don't have to, but it'll just be that much better for you, okay? So let's start in our calculations, okay? I have built in the solutions to this problem, and then we'll do some additional practice ones, okay? So we have a 1,400 kilogram car moving westward with a velocity of 15 meters per second, is going to collide with a utility pole and is brought to rest in 0.30 seconds. Find the force exerted on the car during that collision. So again, write down what we know. We know that we have a mass of 1,400 kilograms. We know that we have an initial velocity of, now look at this, negative 15 meters per second. We are recalling signage use when we are talking about direction. Since this is a vector calculation, direction is going to impact our signage. So since our vehicle is traveling westward, we have to put a negative sign in front of it. Again, all that does is just indicate the direction in which we're going, okay? So, and also it helps us, especially in this case when we're calculating force, which direction the force will be directed towards when we are stopping the vehicle as it travels west, okay? We also know the time frame that this took place in, 0.3 seconds, and we also know that it came to a complete stop, so its VF is 0 meters per second. We need to figure out how much force it took from the pole to stop the car in those parameters, okay? So we're gonna take the formula of F delta T. Again, I just use the one that we were given, but we do not have to include the delta P on there. We can have F delta T is equal to MVF minus MVI. And then we rearrange it to solve for F. And so in doing so, we simply divide both sides by delta T. Once we've done that, we input our known values. Again, mass is in here twice because it's the same vehicle. The final speed, or velocity, we should say in this case, velocity, came to a stop, so 0 meters per second. Again, its initial was negative 15 meters per second as it traveled westward. As we solve for this, again, making sure we keep in mind the units that are going to be involved. So here, before we get our final answer, we have kilograms times meters per second over seconds. So really that gives us kilograms times meters per second squared, which, if we recall from last semester, gives us the unit of newtons, which is the appropriate unit for force. And we find that the force is 7.0 times 10 to the fourth newtons to the east. Again, in order to slow down or stop an object, the force doing so must act in opposite direction of the motion of the object being stopped. So since the car was traveling westward, the force is going to be directed eastward. Okay? Next, I want you to open up your textbooks to page 201. Okay? We are going to do a couple of sample exercises. Again, 201. Gotta get, that's two. Okay, I think that'll be good. Move my coffee. Okie dokie. And let's look at our book here. Okay. Again, we're going to do number 1 right now. Moving my stuff around. So number 1 says a 0.5 kilogram football is thrown with a velocity of 15 meters per second to the right. A stationary receiver catches the ball and brings it to rest in 0.020 seconds. What is the force exerted on the ball by the receiver? Okay, so again, we are doing number 1 here. And first, let's write down what we know. We know the mass of the football is 0.050 kilograms. Again, making sure we have kilograms as our mass. We know that we had a VI, or initial velocity, of 15 meters per second to the right. Okay, so that's going to mean I have just a positive sign, or a known positive sign here. We know that this time interval to stop the ball was 0.020 seconds. We also know that according to the question, that it says the ball was brought to a rest. So the final velocity is 0 meters per second. So we need to set up our formula here. F delta T is equal to MVF minus MVI. Again, we need to solve for F. So we're going to divide both sides by delta t. We're going to get mvf minus mvi over delta t. And now we plug in our values. Okay, so we have our mass, 0.50 kilograms. We have our final velocity, 0 meters per second, minus our mass again, 0.50 kilograms, multiplied by our initial velocity of 15 meters per second. Divide that all by 0.020 seconds. Now, if you want to pause the video and solve this yourself, feel free to do so. I'm going to go ahead and continue working here. So the force, after we calculate this, we're going to end up getting a negative 3.8 times 10 to the second newtons to the right. So that was the direction the ball traveled. But again, we've got this negative sign here. Okay, so like we did back in the first semester, we have to adjust for that negative sign. So really, what that does for our final answer is make it 3.8 times 10 to the second newtons to the left. Okay, so that makes this our final answer. The force, again, the ball was traveling to the right. The ball was brought to a stop. That means that the object that was stopping the ball, which was the receiver, had to act and provide a force that was opposite to the direction that the ball was traveling. Therefore, 3.8 times 10 to the second newtons to the left would be our correct and final answer. Please remember that if you have a negative sign in your answer, you want to remove that and adjust accordingly your direction. Okay? Let's move on to our next question. Let's look at number 3 here. Okay? A 0.40 kilogram soccer ball approaches the player horizontally with a velocity of 18 meters per second to the north. The player strikes the ball and causes it to move in the opposite direction with a velocity of 22 meters per second. When impulse was delivered to the ball by the player. Okay, so what do we know? We know that the mass of the soccer ball was 0.40 kilogram. We know that the initial velocity was 18 meters per second north. And we know the final velocity was 22 meters per second south. So that means this is negative 22 meters per second. Okay. So what are we trying to solve for here? So what we really need to do is this, okay? We know that F delta T is equal to delta P, okay? Impulse is equal to change in momentum. But we also know that that is also equal to mvf minus mvi, okay? So if we know the mass of the object and the initial and final velocities of the object, and we know that they are equal to change momentum, and we also know that the change of momentum is equal to impulse, all we really need to do is solve for delta P. Because once we solve for delta P, that is going to be equivalent to our impulse there. So delta P is equal to mvf minus mvi, and go ahead and plug in your values here. Okay, again, our mass is 0.40 kilogram. Our final was negative 22 meters per second minus 0.40 kilogram times our initial of 18 meters per second. Again, if you need to pause real briefly, go ahead. But we find that we have a change in momentum of 16 kilograms times meters per second to the north. Again, it's going to be a positive value. So what that means is, again, we're going to have a negative value, but eventually you're going to change that negative out and you're going to get to the north. So that means your impulse is equal to delta P, which is equal to 16 kilograms times meters per second north. Again, in your initial calculation, you will get a negative answer. Take that negative sign and remove it and change the direction that is going. Because since you are getting a negative answer on your initial calculation, that would indicate south. But when you have a negative sign in front of your value and a direction of south, you're going to remove that negative sign and change your direction to the opposite, which is north. All right, we'll do one more. Okay, this time we're going to be solving for something different. Let's look at number 4. Let's do 4a because you are going to solve both a and b. You're going to solve for the same variable. All you're changing is the values that you put in there, okay? So let's do 4a. The process will be the same for 4b. If you want to go ahead and do 4b, okay? Oh, nearly lost everything on my desk. Stay. Okay, so 4a. We have a 0.5 kilogram object is at rest. A 3.00 Newton force to the right acts on the object during a time interval of 1.50 seconds. What is the velocity of the object at the end of the interval? Okay, so let's look here. I'm going to kind of adjust some of this stuff here. So we got 4. So we know the mass is equal to 0.50 kilogram. We know that the force is 3.00 newtons to the right. We know that the time interval is 1.50 seconds. We know that the initial velocity is 0 meters per second because it said it starts at rest. And what we need to figure out is the final velocity once all this is done. Okay? So again, taking F delta T equals mvf minus mvi, we need to solve for vf. So when you rearrange this, you're going to get the following setup. Vf is equal to F delta T plus mvi over m. So now, once we've got that situated, we can go ahead and start putting in our values. Our force is 3.00 newtons. Our time is 1.50 seconds. Our mass is 0.50 kilograms. And our initial velocity is 0 meters per second. Now you'll soon start to find out some shortcuts. I didn't necessarily have to put that in here because 0 times anything is going to be 0, but I like to show you everything as I've mentioned many times before. And our mass again goes down here. So once you've got those put in there, you can pause the video, calculate yourself. But when you restart the video, you're going to find that when you calculate, you're going to get 9.0 meters per second to the right. Again, we're talking velocity, so we've got to have direction when we solve for those. So there you have it. That kind of wraps up all the different types of examples that we're going to do. Now, in regards to your homework on problem bank B, here we go, okay? I want you to cross out the following numbers, and those will be the numbers that you do not do. So again, these are the numbers you do not do. Cross out number 4. Cross out number 8. Cross out number 9. Again, cross out numbers number 4, 8, and 9. You are to do the remaining 7. Okay? If you have any questions on this, feel free to email me or message me on Classroom. But until then, I'm calling it an end to the video. Have a good day.